Hello, everyone. Welcome to another security seminar from CERIAS. Today is our privilege to have Dr. Yanju Jia, who is currently a postdoctoral researcher at the Department of Computer Science at Purdue University. In 2022, she obtained her PhD in Computer Science Department from Shanghai Jiao Tong University. Her research mainly focuses on applied cryptography, especially secure computation, blockchain, and provable security. She is dedicated to designing efficient and secure cryptographic protocols that enhance collaboration while ensuring privacy protection. Her work has been published at top-tier conferences such as Usenix Security, CCS, and Asia Crypt. For more detailed information, please look at her website, which we posted in the CERIAS seminar webpage. Thank you for being here. The floor is yours.
Okay, thank you for the introduction. Okay, yeah, I'm Yanju Jia, and I'm a postdoc at the Computer Science Department. Today, I'm glad to give this talk to introduce our recent work, HomeRun high-efficiency Oblivious message retrieval unrestricted. This is a joint work with Warren Wentetier and Professor Aniket Kati. Okay, let's first see what is Oblivious message retrieval. I will use OMR for short. OMR is for a type of communication. Here, the users will communicate via a bulletin board. What is bulletin board? Bulletin board means that this is a public board and anyone can access to the board. And anyone can read the content on the board. And here, if a sender and a recipient want to communicate, the sender needs to submit a pair, including the message and an address. The address is the recipient's address. You can imagine it like your bank account or your telephone number. The address means that only the holder of the address can retrieve the corresponding message. Typically, the blockchain is a specific application of this model, and the blockchain is also a bulletin board. And we can imagine that if there are some transactions and the sender wants to submit some transactions and the transactions is for the recipient, then the sender needs to submit the transaction and including the address. And then the recipient needed to retrieve the corresponding transactions from the blockchain. We know that because the bulletin board is public and anyone can access to the bulletin board. So there are some works focusing on to encrypt to protect the content on the board. Like in blockchain, there are some works focused on designing some privacy-preserving payment protocols. However, we found that even though the content on the bulletin board is encrypted, is protected, it is not enough because the recipient needed to retrieve the message from the board. And then which message is retrieved by a recipient and how often a recipient retrieves the messages from the bulletin board, it also reveal some sensitive information about the recipient. So here the OMR is designed to protect the privacy of the recipient. Okay, actually there is a trivial solution to protect the privacy of recipient, because if the bulletin board is maintained by the recipient, then actually the recipient can just retrieve the message locally, and the recipient doesn't need to interact with others. So it's no chance for the recipient to leak some sensitive information to others. However, this trivial solution is not friendly to resource-constrained recipients because the bulletin board may be very large. For example, here I gave some the size of Ethereum and Bitcoin, and you can see that it's very large for a recipient to maintain it. So there is another solution called server-aided solution. Server-aided solution means that there is one or multiple servers will help the recipient to retrieve the message from the bulletin board. Then in this case, the recipient needs to send some information to the server, and then let the server can send the pertinent messages to the recipient. However, here we need Oblivious. Oblivious means that we need to protect the privacy of recipient from the servers. Specifically, because the recipient needs to use some address to retrieve the message. So the first thing we need to protect is the address of a request. And the second is the linkability between a message and a request, which means that the server can know that there is a request, but the server cannot know which message is retrieved by the request. And the third is that we want to guarantee that even though the recipient used the same address to retrieve multiple times, the servers cannot know that these requests from the same recipient. Okay, now we have known the privacy requirement of OMR. The next thing we need to know is what functions we need. We can imagine that there are always some new messages would be submitted to the bulletin board. And what the servers need to do? The servers need to collect the new messages from the bulletin board and then put the messages into some specific data structure. So the first thing we want to achieve is that if there is a new message, and we want to guarantee that adding a new message to the specific data structure is efficient. And then logically, for the servers, actually the server, we can imagine that the server maintain a mailbox for each recipient. And then what the servers do is to put the messages to the corresponding mailbox. However, according to our privacy requirement, obviously the servers cannot know the linkability between the messages and the mailbox. However, if the capacity of the mailbox is limited, then there may be an adversary. It can just send some garbage messages to a recipient, then the mailbox will blow up. So the next thing we want to achieve is that the capacity of each mailbox is unlimited, which means that a recipient can retrieve unlimited messages. Okay, now we have known the function and the privacy requirement of OMR. At the first glance, maybe you think that we can use PIR, private information retrieval technique to solve the OMR problem. However, there is a key difference between the two problems. Because in PIR, actually the recipient knows the positions of the pertinent messages in the data set. For example, the sender maybe holds a data set including 1,000 messages, but the recipient can know that, the second message is for me. And so the recipient can use the index 2 to retrieve the message from the data set. However, in OMR problem, the recipient just have an address, and the recipient doesn't know the positions of her messages on the data set. And so the key part we need to achieve for OMR is to provide the index to the recipient. And also there are some like key value PIR. However, in OMR, for each address, there may be multiple messages for the address. So even though we use like key value PIR, we also cannot do this. Okay, here I show the existing works for these problems. And we can see that most of the works, they use one semi-honest server, and they use some expensive public key technique to solve this problem. And also, two works, they use one server, but with a trusted execution environment, TE, to solve this problem. TE means that you can trust the environment, and you can't get some information from the environment. So the environment has protected environment to execute some program. And also the second work, they use two semi-honest but non-colluding servers to solve this problem. And they use a general technique called doubled circuit to solve this. Likewise, our work also use two semi-honest and non-colluding servers to solve this problem, but we use some lightweight secure computation technique to solve this problem and achieve a high performance. Okay, let's first see how we can guarantee the basic functions. Actually, for the basic functions, we can use a simple structure to achieve it. Here, the server can maintain this list, and this list includes the pairs of the address and the message. And we can say that if there is a new message, then the server can just end the new message at the end of the list. So it is efficient. And also, because the server can extend the list constantly, so the number of messages for a recipient is unlimited. However, if we use this simple structure to solve this problem, all of the privacy requirements are broken. Because in this structure, the recipient needs to send the address to the server, and so the server can know this address. For example, here's address 3. And also the server can know that M3 is for this request. So the server can know the linkability between the message and the request. And also, if the recipient uses the address 3 to retrieve 2 times, then the server can find that these 2 requests from the same recipient. So next, we will see how we can achieve these privacy requirements step by step. Here we use 2 semi-honest servers, and different from the basic scheme. Here, the 2 servers hold the shares of the addresses, not the original addresses. Like here, the L1 and L1 prime is the shares of the address 1. So holding the share of the address cannot know the original address. And then when the recipient wanted to retrieve the message, the recipient can also share her address. Here's the address 3, and to two shares L and L prime. And send the two request shares to the two servers, respectively. And then after obtaining the request shares, the two servers can compute these two columns to XOR the request share to the stored shares. And in this case, because we assume that the recipient's address is address 3, so these two items would be equal. In this way, we can see that because the recipient will share the address to the two servers, so the servers, one of the server cannot know the address, so we hide the address of a request. And also because the recipient can share the address in different way in different requests, so for one of the server, the server just obtains some randomness. So the two servers cannot link the two requests, find that they are from the same recipient. However, for now, the two servers still know that which message is retrieved by a request. So to solve this problem, we use a building block called the private equality test. Private equality test allows two items as input, x0 and x1. And the PET will compare if x0 is equal to x1. If the two items are equal, then PET will generate two different bits, B0 and B1. Otherwise, the two bits would be equal. Now, for each message, the two servers can use the PET to test if they are equal. However, because the two servers can just obtain the shares of the equality test results, so the two servers cannot know which message is for the recipient. And then the recipient can, and then the two servers can send the results shares to the recipient. Means that they split vectors to the recipient. And then for the recipient, it's easy to recover the results of the equality test. And here the recipient can find that in this recovered vector, only the third bit is 1. So the recipient knows that the pertinent index is 3. And then the recipient can use the PR technique to retrieve the M3 from the two servers. Okay, now we have achieved the 3 privacy requirements. However, there is another issue. Because before, we just think the address is just some string. So if the address is public, then anyone holding the address can request the corresponding messages from the two servers. It also breaks the privacy of the recipient. So here we change, we use some public key to serve as the address. And then only the holder of the secret key can retrieve the messages from the two servers. And here, the recipients, besides the shares of the address, the recipients also needed to sign some proof to the two servers and to prove that I hold the secret key. Okay. Besides the basic functions, in our work, we also, for the first time, to introduce a new feature called deletion. Deletion means that we want to delete the retrieved messages. Because if there is no deletion, then the cost would increase constantly. Because the runtime and the communication cost of the two servers is linear in the messages stored by them. And it's not just for our scheme, also for the previous works, they also has this problem. But if we delete for each request, then the two servers can link the message and the request. So it will also break our privacy requirements. So in our work, we delete once in a period, and we can set the period in advance, for example, 1 day or 1 week. And in this way, we can hide the message and the request link among all the requests in the period. For example, maybe 1 day there are 1,000 requests, and so the two servers just know that this messages was retrieved by this 1,000 requests, but the two servers cannot link each message and each request. Okay, next let's see how we can delete the retrieved messages. Actually, the PT, the output of the PT include the information about which messages have been retrieved. So here we require the two servers to aggregate the results of the PT. For example, here I gave after request 1 and request 2, then the two servers can XOR the base of the PT. But in practice, maybe there are many requests, maybe 1,000. But here I just gave 2 to give an example. And here we can see that the result is 0, 1, 1, which means that the second and the third messages were retrieved by the two requests. However, there is a situation that a message was retrieved twice, because after each retrieval, the message is still there. So if the recipients use the same address to retrieve again, then the message would be retrieved twice. So if it be retrieved twice, then there would be 2 1 bits, and then the 1 bits would be cancelled out. To solve this problem, we introduce unique randomness for each bit to prevent the situation. Specifically, here for each request and for each message, the two servers will get the common randomness. For example, here for request 1 and for the first message, there is randomness R1 1, and then for the second message there is R2 1. Okay, and then for the second request, they will also generate this randomness vector for the messages. And then when aggregate the results of the PT, they also multiply the randomness to the bit. And then we can see that here they can get this randomness result. And if there is another request 3, they also generate this randomness vector to this. And because for each request, the randomness is different, so if there are 2 1, it will not be cancelled out. So here we get the R3 2 and R3 3. Okay, and then Okay, now the two servers can recover the randomness and also the zero. And if they found that the result is zero, which means that the message haven't been retrieved in this period. And if it is non-zero, then which means that the message has been retrieved in this period. So the servers need to delete the message. However, if we just open these results, the two servers can find more information. Because here the randomness is common information for the two servers. So for two servers, for each request, the two servers know the randomness vector. And if they get these results and they find that the second one is R21, and then the server can, according to the results obtained from the PET, to defer the results of the other server's results of the PET, and to know which messages has retrieved by the request. And so after observing these results, the server can know this information. The request 1 retrieves M2, and the request 2 and request 3 retrieves M3, and the request 3 retrieves M4. To solve this problem, we want to achieve that the two servers cannot know the value of this vector. So here we add a building block called multi-point Oblivious PRF. This PRF can guarantee that if the inputs are equal, then the outputs of the PRF are also equal. However, they will generate a secret key K. And then if the server 2 cannot know the secret key K, then they cannot, the server 2 cannot know the input of the PRF. So now after the multi-point OPRF, the server 2 can obtain the results of this vector, and then the server 1 can obtain the secret key K. And then the server 1 can use the secret key to compute the PRF values of these vectors. And then the two servers can compare if the two PRF outputs are equal. And if they are not equal, which means that the randomness will not get the zero, so which means that the message has been retrieved. So in this case, the server 2 can know that M2, M3, and M4 have been retrieved. So they can tell server 1 that, oh, we need to retrieve the 3 messages. Okay, by introducing the deletion, and we can see that we can improve the performance regularly. And here we can see that this blue line means that if we don't have the deletion, then the performance, the runtime would increase linearly. And here means that after each day, we will delete once. And here the retrieval rate means that we assume different retrieval rate, and we retrieve and we delete all the retrieved message. And we can say that if we delete the retrieved message, then the number of the stored messages would be reduced, and then the performance would be better. And so we can achieve a relatively stable performance. And this is the performance of our work. And for example, here the 2 to 18 means that if there are 2 to 18 messages on the bulletin board, here the detector means the 2 servers. Then one recipient want to retrieve a message, then the detector need to run maybe 3 seconds. And also the deletion time means that if we wanted to delete once from the bulletin board, we need 3 seconds. And then we summarize the features of the current works and our work in this table. And we can see that for all of this work can hide the address of the request, because this is the main requirement of the OMR problem. And the link between a message and the request, for means that we can hide the request, hide the linkability among all of the stored messages. And the partial means that we can just hide the linkability among a subset of the stored messages. And the link between 2 requests actually is proposed by our work, but we also analyzed other works if they can achieve this property. And we found that some works also can achieve this property. And for the addition method, because we consider we want to ID a message efficiently, so we can there are 2 main ways to add. One is just append the new message at the end of a list, and the other way is to update all. And also this work, they use a specific data structure to finish it. And they also needed to update some subsets of the list. And apparently, because if you just append the new message at the end, the efficiency is best. And also, we are the first to consider the unlimited message of a recipient. However, we also find that actually these 2 works also can achieve this property. And our work for the first time to introduce the deletion, and we can achieve it. Actually, we also have some extensions for our work. The first is that although we consider semi-honest servers, however, if the malicious behavior of the server is undetectable, we cannot assume that the servers doesn't do this, because it is undetectable. Even though they do this, we cannot find it. So we also consider to resist the undetectable malicious behavior of a server. And also for the deletion, even though we hide the linkability between a message and a request in a period, however, it also reveals that this recipient retrieve this request retrieve message in this state. So we also provide the recipients with an option not to delete. It can depend on the recipient. And also we consider group citing. Group citing means that, like our email list, if the sender sent a message and they can cite a group, and all of the recipients in this group can retrieve the message. And the next is delete according to the PIR request. For now, we delete the messages according to the index request, because we assume that if the recipient once obtaining the index, then they will use the index to retrieve the message from the 2 servers. However, in practice, maybe some people first get the index, but maybe wait for 1 day and then to retrieve the message. So we also discuss how to delete according to the PIR request. Next, I will give some more details about the first extension. Okay, so for the first extension is about resisting undetectable malicious behavior of a server. Specifically, in our previous scheme, we assume that the two servers will not collude with the recipient, and then the two servers can need to verify the proofs from the recipient correctly. However, if one of the servers collude with the recipient, for example, here the server 2, and even though the recipient gave a bad proof to the server 2, and the server 2 doesn't verify this proof, then the recipient can retrieve the message for any address. Because even though the recipient doesn't know the secret key, the recipient can generate one of the proof. So to solve this problem, we use a technique called one-time address, which means that even though the recipient knows that there is an address, however, for this address, there will have a one-time address for each message. For example, I have an bank account, and maybe you know the bank account. However, for my transaction, we use a one-time account for me. And the one-time account can link to my account, but just me, because I have the secret key, so only me can find it. And so here we refresh the address for each sending. And in this way, that the recipient, even though they know the address, but if that doesn't know the secret key, then they cannot know the one-time address. Okay. In summary, in our work, we achieve a new Oblivious message retrieval solution, and this OMR solution has the 3 features. One is that we can achieve a high performance, and the second is that the number of the messages that a recipient can retrieve is unlimited. And the third is that we support the deletion for the first time. And also, this is my homepage, and we put our source code on the GitHub, and you can scan the QR to obtain them. Okay, thank you.
Thank you very much for the talk. So basically, I would like to ask in-person audience or online audience to pose your questions in the Q&A. In the meantime, until we get some questions, I have some for you. So you mentioned initially the concept of shared addresses.
Yes.
So when you mention shared addresses, I'm assuming that in practice, your protocol will be carried over a network of connected hosts, right? You have a server, you have a client. So the address that you are talking about is what kind of address exactly?
Oh, the address actually is some how to say in this situation. If you know, like the blockchain on the blockchain, and maybe you can imagine you just have an account, like your bank account, and this is some numbers, right? But the shares means that you can share the the numbers
I see.
and to separate the numbers into two shares. And if one server obtains the share, for one of the server, it's just some randomness. It's meaningful.
Right, exactly.
Yeah, and only when the two shares combine, then can recover the address. And here the address is just for, you can say identification for each recipient. Yeah, like our student ID or like telephone number, like this. Yeah.
Okay. Oh, thank you. Okay. So another question would be, so you mentioned some comparison of your approach compared to existing literature. I was wondering, indeed, it's state of the art in your case, from the perspective of key generation, storage, the amount of information required to be kept for successful communication. Have you checked, does it require a lot of storage space from the perspective of the endpoints? How much information do I need to keep to carry out all these tasks, the deletion, the retrieval, and so on?
Okay. I don't remember if I gave the...
No problem. Yeah, it's just, okay.
Yes, because here for the two servers, they just need to store the messages and the address, all of this. And it depends on how long your message is.
Yeah.
Yeah, and they don't need to store anything else.
Okay,
just the address and the message. It depends on the real situation.
I see.
Yeah,
Okay.
and here in this table we gave the real-time cost. Yeah, the communication, like the two servers, also need this communication cost.
I see. Oh,
yeah.
Okay. Okay. So are you saying also that the length of the message, does it impact also the size of the keys, or is it irrelevant?
Sorry?
Is it the size of the messages also impacting the size of the secret keys as well, or they are not associated?
Oh, no.
Okay,
they
great.
have no relationship.
They have no relation.
Yeah.
Okay. I don't see any questions from the online audience. If anyone wants to ask a question, okay. 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 Right. Okay, great. Thank you. Let's thank the speaker.
Thank you.
Thank you very much.
Thank you.